Hi everyone, in this video we will go over Outatime, a cloud gaming service, and we will talk about why we will need to use Outatime, what is currently out there, and what's the motivation behind it, and how the technology works. My name is Venkata Harish Kajur, and my partner is Neha and Soni, and we will go over Outatime. Okay, let's talk about the motivation behind Outatime. Currently, gaming is one of the most popular leisure activities among the youth. The biggest deal breakers to most video gamers is to truly enjoy the games that they have purchased. Most of the games require sophisticated hardware in order to enjoy them. In order to purchase a computer with those kind of specs, you could easily spend $1,500 to $2,000. Unfortunately, not everyone can afford such high-end computers. And for those who can afford those computers, you still have the problem. Every couple of years, every 4 to 5 years, you're gonna end up upgrading your computer to the latest model, and that could cost another $2,000 or $3,000. And the main reason for that is because as the hardware that requires the same the newer games require more sophisticated hardware each year, and they're and every some hardware that was really fast in 2005 won't be the same like in 2010 might not be. And that's where the biggest problem arises. How do we play the games without having to buy high-end computers? Because I mean, low-end computers can play the game, but it's just won't they won't process the same, and it's going to be slower. The graphics won't be rendered properly, and it won't give you the same experience as you get with a high-end computer. And now, how do we play a video game without having high-end computers? That's where services like OnLive and other cloud computing services like PlayStation Now comes into play, where they provide services for you to be able to play a video game on any computer, as long as it has decent specs, like decent video encoding and decoding. As such, it require basically it sends the user input to the server. The server, based on the input, based on the current frame, it will render the future frame and sends it back to the end user. This is great, but the problem with technologies like this is there are very high latencies, especially when there's high usage, and when there's it could when it works really great, but there are lots of times where things slow down, and it just freezes up. It doesn't work the same, because most of the processing is done on the server side, and by the time the client receives it, it's just it makes most gamers who wants to play it gives you almost the same kind of problems with having a standard computer. It's just a lot of times you just won't be able to enjoy the game as much as as you would with a high-end computer would. And that's where services like that's where Outatime comes into play. What Outatime does differently from standard cloud gaming services is that it has a way to speculatively execute multiple possible frames. So based on the current input, and based on based on the current input and the current frame, it will see what are the possible sequential frames that can happen based on this input, and it predicts them ahead of time, and then it sends that frames back to the user. And then it also has a way of handling dynamism and sensitivity in graphically intensive games. The way it does that is using these four techniques: future state prediction, state approximation with image-based rendering, fast state checkpoint, and state compression. Okay, what are the goals of Outatime. Main goal of Outatime is to have a low RTT time, less than 32 milliseconds at high frame times. And how it plans to achieve this is to generate possible outframes and transfer them. What do you mean by that? Basically, if you look at the image on the left, you have a standard cloud gaming, how client and server interacts. Basically, inputs is in this example, input 5 is sent at time 5 and it's received at time 7 on the server side, and then it renders the frame 5 and then sends it at time 8 and then sends it back to the user at time 10. This is how long the frame time takes. It could take like 5 ticks or however, and that could be my 160 or 200 or 300 microseconds or longer. And let's look at how Outatime tries to achieve this. At T0, input 0 is sent to the server. At T2, the server receives it, and then it processes, based on input 0, what is the possible sequential frames that it could possibly be able to get based on your own actions, based on people with your level skill. So as more users are playing the game, it will be able to better predict what your action could be and generate the frames for each of those possible sequential inputs, and send those frames back to the end user. So at T5, the user doesn't have to resend another request to the server for the input frames. It will automatically have them because it already predicted what you would possibly send. Let's talk about speculation for navigation. What does that mean? It predicts a sequence of future navigation input inputs. It refines the prediction based on the expected error. So if the error is less than less than a certain, when expected errors are low, it applies a traditional Kalman filter to reduce the shake. And if they're really big, it uses misprediction compensation on the client side to process the frame. Okay, let's talk about what I mean by shake reduction. Okay, sometimes misprediction can create a very distracting visual effect as a video shake. Because let's say that the server side predicts that the user will be at x plus 2 degrees, x plus 3 degrees, y plus 3 degrees, and z plus 7 degrees. But it's actually that the actual was x minus 2 degrees and y plus 2 degrees and z plus 3 degrees. This could make it look like, even in a small degree in miscalculation, it can look like the video was actually shaked. It can make the video look like the screen of the angle that the current video is could be tilted, and it can give a really shaking effect when you're playing the game. And we use Kalman filter to compensate for that video shake in cases of where this misprediction happens. And if the expected error is like greater than expected error, then we use techniques like image-based render. So what I mean by that is, let's say, for example, misprediction can be high if the round trip time is greater than 40 milliseconds. Because the more time it takes for the server to respond back, the more possibility that the next input could be wrong. And it compensates it using image-based rendering. So what it means is, for example, if you look at the image on the left, this is the input image. And based on this input image, it also sends the input depth back. So when this input image is given back with this input depth, the client side can render possible navigation input. So for let's say if the prediction was to move right, it using the client could predict it to move left. The client could render it to move left instead by using this depth information to generate this output frame. And this works very well with navigation inputs. There are two types of actually inputs: navigation inputs and um, impulse inputs. And this is what happens when like there's a misprediction in the navigation input. And another way to resolve it is like using clipped cube image. So what it means is, let's say this is where you are in the center. That's your focus. The camera is pointed at. What if you predicted it to move right, but what if the server predicted to move right, but you actually move left? So what server side could do is actually send all of these frames back and to be able to calculate it on the client side itself. But that could be really inefficient. So what it does is it adds enough metadata, like in this dotted rectangle that you see here. It adds this this metadata back with the main frame, so that if any misprediction happen, it could be resoluted in the client side. And now my partner would go over impulse.
Now let's talk about how do we speculate for impulse event. The example of an impulse event would be a gunfire from a player in a video game. An impulse event is registered after an input from the user is activated. Now what does that mean? Suppose for moving forward, the player inputs or presses a key A. When the input from the user is registered, at that time the input event is activated. Now the main goal for Outatime while speculating for impulse event is to provide output for the user's input as soon as possible to avoid visual inconsistencies. The procedure that Outatime follows is, first the server produces a speculative input sequence beforehand. Now what is beforehand? That is, suppose if the event is going to happen at T1, all the input possibilities by the client is calculated at T0 itself. And this is what calculating input sequence beforehand means. Then the final frame is rendered for each of the speculated input frame. After this rendering is done, the set of the speculated input frame and its corresponding output frame is sent to the client. Now after the client receives the set of the input frames and the corresponding output frames, what it does is it matches its actual output with the speculated input and displays the output frame for the matched input frame. Now the only drawback with this with speculated event is, as the round trip time increases, the number of possible sequences grows exponentially. Now suppose the round trip time is 8 ticks. So there will be 2 raised to 8 possible sequences. Now to tame or to reduce the number of possible sequences, that is to reduce or to tame the state space explosion, Outatime uses subsampling and time shifting. Now what happens in subsampling? In subsampling, we reduce the number of sequences by only permitting activation at the subsampling periodicity. But the drawback with this is that there may be chances when the activation won't fall in the sampling periodicity, and then the activation will be lost, which can be counterintuitive to the user. To avoid this drawback, we use time shifting. Now why is time shifting used? Because of the drawback by the subsampling. So what happens in time shifting? To align the activation with the subsampled tick, we either move the activation forward or backward. That is either earlier in time or later in time. It is always feasible to shift the activation earlier in time so that the shift actually occurs on the speculative sequence at the server rather than the actual committed by the client. That is the actual sequence committed by the client. Now here is an example of time shift, a simple example of time shift, wherein it showed that the activation occurred at T1 and the activation occurred at T2 are shifted forward to T3, while the activation occurred at T4 is shifted backward to T3. Now let's talk something about advanced impulse event. Now what is advanced impulse event? In binary impulse event, that is whatever we have discussed till now is binary impulse event. So there are only two possibilities or two-stage branching factor. That is either the activation has happened or no activation has happened. But in advanced impulse event, it could be ternary or quaternary. There is more than two branching factors. That is, if it is a ternary impulse event, there can be three branching factors. If it is a quaternary then there impulse event, then there can be four branching factors. So this was a gist about the advanced impulse event. Now let's talk about delay tolerant event. What is a delay tolerant event? A delay tolerant event is the event that are slow as compared to the round trip time, and they are called as delay tolerant event. These events have a very high cooldown time. Now what is a cooldown time? A cooldown time is a period after an event is registered and no other impulse event can be registered. Now one of the example we can say is a weapon gun reloading in a video game. Now let's take an example. Suppose this delay tolerant event was supposed to display n number of frames, but happened to miss or lose some frames due to RTT. Now to avoid visual inconsistency because of the missed frames, Outatime follows the approach of compressed time, wherein the time is compressed by sampling the remaining frames, which gives an effect of fast speed. And the example for this can be a weapon switching or a weapon reloading immediately followed by firing is handled correctly. And this is the advantage of compressed time when the delay tolerant event happens to miss out some frames due to RTT. Let's talk about fast checkpoint and rollback. Now Outatime uses checkpoint and restore to play forward a speculative sequence, and a rollback is used to go back in time if the speculated sequence is incorrect. For doing so, Outatime uses hybrid of page level and object level checkpointing. Now in checkpointing, only those objects are checkpointed that bear some output or reproduce the world state. The objects which don't do so or which don't bear any output aren't checkpointed because there is no use of doing this. Talking about a rollback, in page level checkpointing, when a page fault occurs, the allocator makes a copy of the page and marks it read only. Now in order to correctly roll back, the allocator copies the original content of the modified or also we call it as a dirty page using the copies it created, and it successfully rollbacks using page level checkpointing. Now let's talk about object level checkpointing. What happens in object level checkpointing for rollback? Now for rollback in object level checkpointing, we delete the objects that did not exist at the checkpointing and restore the object that existed at checkpointing. For example, consider at checkpointing there were two objects A and B, and after the checkpoint we added another object C. So to correctly roll back, we delete the object C that wasn't present at the checkpoint. Bandwidth compression. Now transmitting the speculated frames generates an additional overhead while transmitting it from server to client instead of just sending the exact one frame corresponding to the user's input. Now how do we reduce this overhead? To reduce the bandwidth or to reduce the overhead of the bandwidth or to reduce the bandwidth, Outatime takes an advantage of spatial and temporal coherence. Now how does this work? Let's see how does this work. Each frame is divided into macro blocks, that is small blocks. It could be 64 into 64 bit. It is just an example. It could be of any size. So each frame is divided into macro blocks. Now we search for macro blocks that are equivalent between different frames. And once the equivalence is found, only the first macro block is sent, and the pointers are used for other equivalent macro blocks. And this is how the bandwidth compression is done in Outatime. Now all these discussion regarding Outatime was done relating to single player, but Outatime also supports multiplayer. Now in multiplayer gaming, we use dead reckoning, which is a process to calculate one's current location by using the previously determined position. So for multiplayer gaming, except for thin client and the server, we also have coordination server. Now what happens is a client sends its current location using dead reckoning to the to the coordination server, and then the coordination server sends the information of that client to all the other clients to produce a consistent view. And this is how the Outatime works with multiplayer gaming. Now the rest of the part would be continued by Venkatesh Harish.
To prototype Outatime, they modified Doom 3 and they ran the modified versions on 4 servers, 1 master and 3 slaves. And each of the slaves can accept these commands: advance, render, undo, commit, and render cube. Advance is simple; it just moves the game forward, next logical step. Render renders the frame based on the state and the given input. Render the frame. Undo discards any uncommitted state. Commits the input, makes it permanent. Render cube, which we talked about with the crypt cube image and the IBR image-based rendering, produces the cube map and the depth map. So if a prediction failed, the client side can generate the visually generate the map based on the metadata given by the cube map and depth map. Now let's talk about the evaluation. They did uses. So the way they did the studies is they took in 2 groups, study A and study B. Study A had 23 average gamers and study B had 18 experienced gamers. And the way they set it up was they had a standard thin client which uses cloud computing, and they had standard thin client with Outatime, yeah, using cloud computing, and they also had a thick client without Outatime. It's just going to be the client had the I mean, wherever the client was running, it's actually running the whole game in the server. And in order to simulate the RTT, because we can't change the RTT, they actually had the client process and um, the on the wherever Outatime is running on the same server, but they simulated what the round trip time would be by modifying the code, and they tested the results to see, and also the both the people who would uh, taking the who were playing the game and who conducted the tests for this weren't aware if they were playing either the thin client with cloud computing, or if they're playing thin client with Outatime, in order to make sure the results was not compromised. And based on the evaluation of those people um, who took who took the studies, this is what they noticed. Their opinion for Outatime was pretty high, compared to standard thin clients, and it's actually in par with having a standard thick client. If you can notice on the image on the left, most people found that usually it actually that average gamers actually barely even noticed any difference between the thin client thin client with Outatime and a thick client. But obviously, advanced gamers did find differences, that they did notice that this is they did so notice some glitches here and there, but more or less the response time was pretty good. And if you can see the round trip time on average, Outatime does so much better as the round trip time increases, and and conclusion, basically, what we can conclude from this is, based on the studies they have driven, based on the research we did online, we can conclude that this is a very practical technology. Once implemented and fully utilized, this could be the future for cloud gaming, because everyone who played the game found that this is actually favored the Outatime compared to other cloud gaming providers. And thank you.